Part 5 of the Introduction to Standardized Echography especially deals with the reflection of ultrasound at large acoustic interfaces. In this part we also explain the importance of high-frequency nodules for the differentiation between smooth and coarse large interfaces. Acoustic tissue interfaces separate spaces of different acoustic properties, that is, density and sound velocity. Important is the size of these interfaces in relation to the wavelength lambda. Large acoustic interfaces are those with a diameter of greater than half a millimeter. Small acoustic interfaces are those which are smaller than half a millimeter. And all this in the viewpoint of 0.19 millimeter of the lambda in tissues when we use the 8 megahertz that are used in standardized A-scan for the tissue differentiation. And then we have extremely large interfaces that are larger than half a millimeter, but they behave basically like the large ones. And we have extremely small ones that are smaller than 50 micron. We cannot resolve them with the lambda of 8 megahertz. Extremely large and large interfaces cause reflection. We already discussed that the incident sound beam, the continuing sound beam, and the reflected sound beam, they all lie in the same plane. The angle of incidence is the angle between the incident sound beam and perpendicular to the interface, and the angle of reflection is the angle between the perpendicular to the interface and the reflected sound beam. And now I come to the term reflectivity. Physical definition of reflectivity is the ratio between the reflected energy over the incident energy. We cannot use this term and reflectivity with this physical definition in diagnostic ultrasound, because we can neither measure the incident energy nor the reflected energy. So we use a clinical echographic definition of the reflectivity. It is the percentage of the maximal height of an individual echo spike, like here the surface spike of the malignant melanoma here, as percentage of the display height, 100% in this case, or the average height of all the echo spikes from within a tissue here within the malignant melanoma as percentage of the display height. That's about 40% in this case. And all this can only be used at tissue sensitivity. At other sensitivity settings, this clinical echographic definition is worthless. So tissue sensitivity is a must. We are dealing with maximum echo intensities when the beam is perpendicular. Here the beam comes in, perpendicular exposure at this interface, and the reflected portion, the echo, is maximized this way. And it depends on the reflectivity of the interface whether this maximal echo intensity is large or small. When we're dealing with large, smooth, mirror-like interfaces like here, then when we angle the incident beam, much, or in this case all, the reflected energy does not return to the probe, is reflected away. We cannot see this interface in this sound beam direction. And extremely large, smooth interfaces of this kind are the two corneal surfaces, the two lens surfaces, and the retinal surface. They are smooth and behaved this way. Large coarse interfaces not only reflect but also scatter the ultrasonic incoming energy. We still have the maximum echo when we are aiming a beam perpendicularly at this interface. But this maximum echo will be weaker than from a smooth large interface of the same reflectivity. And when we now angle the beam, we're not losing the echo entirely. Yes, the maximum energy is still bypassing the probe and not visible, but some energy is scattered back to the probe so that we still see an echo, a weaker one. And such extremely large coarse interfaces in the eye and orbit are, for instance, the PL surface of the optic nerve, a very coarse surface, the dural surface, the surface of the muscle sheaths, and the sclera. When we look again at different angles of incidence, at a smooth interface, very quickly the echo signal is weakened or disappears entirely. In a coarse interface, the echo signals weaken, but we see, even with oblique sound beam incidence, still echoes from that surface. And here is an example, a plexiglass surface that is coarse, examined in water. And we see here the water, plain baseline, and then with perpendicular exposure the surface of the plexiglass. The signal is high, And when we have a smooth plexiglass surface in water, this echo spikes looks clearly different from the previous one. Here we see a number of high frequency oscillations, we call them high frequency nodes. Here we see a very smooth line, because with a smooth surface the echo very quickly rises to the maximum, whereas here there is a continuous rise to the maximum. And that is the difference between smooth and coarse large interfaces. And when we angle the beam, as is shown here, then of course we still see this echo being very strong from the coarse surface, from the smooth surface, very weak already, and a little bit more angling it disappears, whereas this is still present. Of course, the distance between the initial spike and the echo signal increases because the distance is larger here to the interface than here. There is an important clinical application of this observation. A detached retina has a smooth surface, whereas a dense membrane has a coarse surface. Now both may give the same or similar echo intensities. But the differentiation is done by observing the left ascending limb of the large surface spike. Here we have the retina. It's a smooth surface, and when we maximize the signal, then this spike rises from the baseline up to the peak very suddenly, a thin, smooth line, interrupted here only by two high-frequency nodules, remnants of the high-frequency oscillations that were filtered out. It's the left ascending limb. The filtering of the high-frequency oscillations is an important part of the signal processing. Besides the amplification, according to the amplifier characteristics, the S-shaped curve, the signals are rectified. That means only the positive amplitudes are shown. The height of the amplitudes is limited with the display height, and the ratio of horizontal and vertical screen expansions is determined. But here we are with the filtering of the high frequency oscillations. You see here the rectification and the high frequency filtering only to a certain amount, not totally. And here we see that again the rectification and the signal, the high frequency signal filtering. If the high frequency wouldn't filter that much, the echo signals would go under, would be drowned by the high frequency. And again, the difference of the maximized echo signals from large plexiglass surfaces, smooth, sharply rising thin line, coarse, many high frequency oscillations, nodules. On the smooth echo signal, we see here only 2 high frequency nodules. On the coarse one that rises slowly, there is much more high frequency occurring before the peak is reached. We see a huge number of high frequency nodules. The clinical application is especially used when we differentiate a detached retina, which has a smooth surface, from a dense fibrovascular membrane, which has a coarse surface. By aiming the beam perpendicularly at either surface, we get maximized signals from these structures, and then the left ascending limb of the retinal spike has 1 to 2 high frequency nodules only, whereas a fibrovascular membrane spike, when maximized, has on the left limb at least 3, sometimes many more high frequency nodules. This is done automatically with the A1 software. All the examiner has to do is aim a perpendicular beam at the questionable surface, and the instrument gives the answer whether it is a detached retina or a dense fibrovascular membrane. A similar situation in orbital tumors. Cyst walls are smooth, tumor capsules are coarse. And another application is the differentiation between the smooth anterior lens surface and a coarse iris surface when the pupil is not dilated in axial eye length measurements. The only